topic area that's dear to my heart, being a modelling referent. A paper written jointly between Arcadis and Semtech. We've only got a couple of the representatives. There's about 5 authors on this paper. 2 of them are here today. So please welcome to the stage Harmen and Henry to present their paper, Enriching Model-Based Systems Engineering with Interoperability Through Master Data.
Good morning, Incozy UK and Incozy Global, if there's anyone from outside UK. So quick overview of our paper, our presentation in a slide. So Harmen will present part 1, which is the fundamentals. So a bit about the core knowledge of MBSE and domain models that's relevant knowledge for our paper. In part 2, we'll talk about how we've enriched the model-based systems engineering process with master data, specifically object type libraries, and how we've done this on high speed 2. And Harmen will present that. And then part 3 is how we've improved on MBSE with the object type libraries again by using linked data. And we'll talk about how we've done this on the Flemish Tunnel project, which is in Belgium. So now I shall pass it over to my colleague, Harmen.
Thanks, Henry. And also from my end, thanks for this opportunity to present. So in this first part, I just wanted to go through a few, what we call them fundamentals, but just to set a bit of the scene on how we build up our paper. And before we go into the 2 use cases that we have. And those 2 use cases are all sounded about, okay, how have we used library data around requirements and other systems engineering information systems, an application on like on project levels. So for this slide, and it slipped a bit through, but like what I want to stress out, what we are using in this paper for these 2 projects, what we use models for is to have descriptive models. So we don't do any predictives with it, but we use for our approach in this paper and on these projects, descriptive model to make sure that we are in control of our systems engineering information, assure quality, but also to make sure that we are able to reuse information on across our different projects. So why are we using model-based systems engineering in this case, and in this case with the definitions of a descriptive model? What we see across our projects at Arcadis, but also across the whole supply chain, is the multidisciplinary challenges on large infrastructural projects. Those projects are getting more and more complex these days, not only because of the locations where they are based in with existing situations, not only because of the technical challenges and the scale of the projects, but also the frameworks that we are working with on these kind of projects, with a lot of joint ventures, a lot of a really big supply chain to actually deliver our projects. So to increase like a coherent view, a qualitative view, but also at the same time timely and reliable information, model-based systems engineering is something we use to make sure that we assure the quality of our designs, we reduce ambiguity, optimize our systems engineering processes from an efficient perspective, and also improve like our technical assurance side of things. But what we also notice when we are doing this is that in the software applications we are using, we we have options to improve like the mechanism for information exchange. But at the same time, it also continues to pose challenges. Challenges of that, like every piece of software has their own way of exchanging data, has their own formats. So we are also looking into ways of how we can improve basically the interoperability of our information. If we want to achieve something like that, we have to address a few things. First of all, we have to address like the lack of standardization in our design processes, in our systems engineering processes. There are great standards, and but to what kind of level do you need standardization so you can make it work for your project level? The lack of interoperability. How do we exchange information across different systems engineering information across different applications that we are using? And also we need to address the lack of the meaning of the data, that we're not just pumping data around, but that we also understand if we share data, information, that not only us understands the meaning of the data when we read it, but to make sure that also the computer understands that. And well, confusions are easily made. Think about a railway, which is a part of a track, but here comes the sun. The Beatles is a type of a track. So how does the computer know? So that is basically what we are trying to achieve here. And when we implement model-based systems engineering on projects, the core for us is always in our designs is like, okay, we work from an objectives to a function, to like function fulfillers, object systems. And we model this with all the other systems engineering information in an information model that we use on projects. So with an information model, we move away from like a document-based way of documenting all of that. We have like a standardized model on projects, a systems engineering model based on the ISO 15288 that we are using across all our projects. Then, and that's where we're going to focus on from now on, is we want to make sure that we can reuse information out libraries. And that is basically the master data. And some of them are purely OTLs. So our first use case is not a true OTL, but just master data on a specific project. And our second case will be around an actual OTL. To achieve that, of course, you need to make sure that you have your ontology, your model on your project level in order so you can map your ontologies with the library information. Okay, then having said that, I would like to dive into the project that we've done, the High-Speed 2 project. And disclaimer for the first slide, that those numbers on the top are probably not correct anymore. But what is correct is the last bit of the slide, which describes a bit about our civils contract project, which sits between London and Birmingham. And it mainly contains like civils. So we have like viaducts, earthworks, bridges. So you can say that we have like, but also highways. So we have like 60 plus of those different asset types or object types, like standardized things that we are building across the whole route. But we have 4,000 assets, so instances of those object types. So we have 17, from the top of my mind, 17 viaducts, for example, in this piece of contract, as part of those set of 4,000 unique assets. You can go on with earthworks, highways, another type of bridges, balancing ponds, drainage, and so on. But the point, of course, is that it's quite interesting to do a lot of your design work on those conceptuals, those object types, and then see how you can apply that on your unique assets from a time-saving perspective, but also from a consistency perspective. Well, the other aspect is that those 4,000 assets are grouped in multiple work packages. So we have those 4,000 unique assets are delivered to the client, to HS2, together with the supply chain and the contractor to high speed 2. So how do we also make sure that that from a work package perspective, all that information is delivered in the right way? Well, and why did we choose then to use, first of all, model-based systems engineering approach, but also like the master data approach, is the number of required assets. So we have 4,000 assets. So how do we make sure that if HS2 receives like our design for a viaduct, our technical assurance for a viaduct, our verification results for a viaduct, that are probably designed across multiple organizations in a joint venture, that they get exactly the same quality and the same information. So we want to make sure that we hit the quality for those required assets, no matter who of the supply chain, who in like the whole delivery organization is actually working on that piece of our project. And then the number of requirements, of course, so okay, how do we make sure that our technical requirements, around 1,000 plus standards, but also like our more stakeholder-related requirements, environmental requirements, are met. So that is what we are focusing on that piece. So what we've done on High Speed 2 then is we developed like a master data set. That master data set was its first step, as everyone should do, of course, is a proper design. So what we did with function analyzers, with our design leads, with our systems engineers, we made a systems architecture of all our design, captured for the purposes like in a decomposition, in a part of a relationship that describes, okay, if you design a bridging structure, or if you design a highway, this is what it should contain of. So the next step, to make it also to increase basically the efficiency of the work we're doing, we introduced like also a taxonomy, a specialization tree, where we basically said, okay, you have a bridging structure, a type of bridging structure can be an overbridge or underbridge. Underbridge can be viaducts, real underbridge or underpass. And basically the next step after that was that we allocated our requirements to those objects in the decomposition or expressed in a taxonomy. And the thing that we also introduced in here was the inheritance. So if we said, okay, if you have a bridging structure requirement, that also applied to an overbridge and underbridge, but also in the case of a viaduct, the requirements of a viaduct were a collection of a viaduct and underbridge and a bridging structure. So that was the approach when it came to developing a library, a set of information with requirements that we can then apply across all our assets. And that was basically the next step. So from the allocation of our individual assets to our object types, we were able to push all our design information, thinking of like requirements, but also predefined verification plans, but also other information like assumptions, departures, design decisions, throughout this whole chain to our unique objects. So a benefit of this was that like we ended up with like a consistency around, okay, if you have to design this viaduct, that you have this consistency about requirements, design decisions, assumptions, departures, and so on, with both like from a master data perspective, but also, of course, geographical specific information allocated to those unique object points. Then the next step was basically that we allocated those unique objects to like work packages. And as you can imagine on a project like this is that we've been working on it since 2017, that the delivery schedule is impacted by changes, information that is not available yet, design decisions that are made that will change basically the packaging of our work. So what we also did is we kind of separated the technical work from like the delivery piece of our information. So an asset could move easily between the different work packages without having to retag any work package related information, because all the work package information was tagged to the individual assets that were easily moving, that we could easily move between the different work packages, and therefore without losing any systems engineering information throughout the whole project. So then so that was kind of the approach that we applied. How does this work in practice? Like, so our designers, our engineers go into like a model-based systems engineering platform. They find up their assets, or they go via work package view, find all the information, and can work from there with the right set of requirements, but also enter their verification results into the system. And then when we actually deliver our information from out of the system, it's consistent current. And when HS2 is opening a packet, they will find the same information against that viaduct, with specific, with of course specific additions per viaduct when required. But at least they knew, okay, this is what I get, and this is what I receive per work packets, without too much effort from our end in quality control, because everything was predefined. So what are a few results on that? So although like our main purpose was making sure like that we achieve like a quality across like packages across our whole design, we managed to also make time savings. Time savings on the thing that I explained around the allocation of assets to work packages. So as soon as we got changes instructed, via all the mechanisms, the assets were like allocated to new work packages. So without losing any or have to redo anything of like the work package information. So that was just basically packaged up in an automatically way, but also time savings, where we had to do over 60,000 verifications on the project. And one of the things that we had to deliver is that we have to include all the requirements for every work package. So what we did is based on our master data set and based on which assets are actually sitting in a work package, we were also, and which requirements belong to that work package, therefore, we were also like able to automatically detect which requirements are not applicable to a certain package. So instead of like asking like our designers and engineers to do this for every single work package, that was all done via the model that we've used. And that ended up in 1,200 hours saved, only for scheme design. We are now in detailed design, and I'm hoping to make a same kind of calculation at the end of detailed design. So this is what I wanted to share about the HS2 use case. Henry will talk a bit more around how we moved away from doing this all on one project and basically having this master data approach on a project level to a use case where we have done it across multiple tunnels with different projects, and therefore also introduced linked data. And over to you.
Okay, part 3. So in part 1, we talked a bit about the fundamentals of our paper, model-based systems engineering, some of the problems such as a track consisting of Beatles songs, Here Comes the Sun, and how you can enrich that by using master data. That was part 2. In part 3, we've gone again a step further. So enriched model-based systems engineering with master data, object type libraries, improving that again with linked data, and specifically on the Flemish Tunnel project. So what is the Flemish Tunnel project? Okay, firstly, the Flemish Tunnel project is in Flanders, the northern region in Belgium. There are 20 tunnels in that region that are in different states of condition. So some of those tunnels were built between 50 to 60 years ago, and they need renovations. When these tunnels were built, they were built to different standards. So there's a national tunnel standard in Belgium, and there's also Atlantis tunnel standard. So there's a city, Antwerp, and they're building a ring of tunnels around, or a ring of roads around Antwerp. And part of that ring of roads, there are some tunnels. And so for that area, they were designed to Atlantis, the government organisation standard. So the situation is different tunnels, different states of condition, needing repairs, designed to different standards. So what was Arcadis and Semtech's role in this project? So we were contracted to the Flemish Agency for Roads and Traffic. I'm not going to pronounce the Dutch name for that. So our job was to firstly document the existing state of the tunnels. So we built a digital twin and categorised the tunnels, how they were currently standing, what condition, and capturing that in a digital twin. Then we produced a new standard. So in addition to the 2 standards that the tunnels were designed to, there's a European standard for tunnels. And though that standard as well has come out since the tunnels were built, and so now there's 3 different standards. So Arcadis developed a standard for the Flemish Agency of Roads and Traffic that the tunnels could then be redesigned or renovated to. And then there's a digital twin for the proposed state. So once we have the current state documented, a set of rules, a standard, and how to update them, what the updated tunnels should look like, including in a digital model. And then that enables the asset management of those tunnels. So for example, if you have a light system that's failing and a tunnel ventilation system, how do you know which one to prioritise? Well, once you've documented everything and you know what the standard says, you can make the best decisions. So that's a bit of an overview of the project. Now, what is linked data? Quick show of hands, who here knows anything about linked data? There are, I count like 6 hands up. Okay. So linked data, this is the first and only time I'll read directly off the slides. Linked data is a set of design principles for sharing machine-readable interlinked data on the web. So basically, it's a set of rules on how you should structure your data. It's important to note that model-based systems engineering, you can have model-based systems engineering without linked data, and you can have linked data without model-based systems engineering. But what we've done is pull them together. So why use linked data? So the big reasons for using linked data is it's software independent. So you can have two different organisations on the same project using the same software, or using different software, but still having the data work correctly. It's meaningful to machines. So we already talked about the importance of having data. Like if you want to automate something, in order to be able to automate it, you need a machine to understand that data. And then finally, it's interoperable via the web. So it doesn't matter if it can be software independent, if it's not interoperable. They're going to need to work together. Okay. So how does linked data work? So this is as technical as I will get. So on the right-hand side, we have a relationship view. So this is how you would, as a systems engineer or a human, would see it. So we have, for example, tunnel 1. So 20 tunnels. Tunnel 1, it is a type of tunnel. Tunnels consist of things like vents and lights and portals. And those portals, for example, that's a subpart, consists of other subparts or sub-subparts, frames, walls, roads. But if you put that into a machine, unless it's a ChatGPT or something, it won't understand that. So how does linked data look to a computer? So linked data is expressed using URIs. URL, for example, I think we all know that, is a type of URI. So for example, tunnel 1 is a type of tunnel. To the computer, that would look like tunnel.com, that's a node. There's a relationship link between them, so that's another URI, and then the end node. And each node can have many different links to many different other nodes. But basically, by expressing this in the linked data principles, you end up with that software independent, interoperable data that we talked about. The view on the left, you don't have to worry about it because, on your projects, you'll just see it through the software in a nice relationship view. Okay. So on the Flemish Tunnel project, what did it look like? So you can see this is similar to what was presented on HS2, a similar object type library structure. Requirements have been allocated to object types, and then they get allocated to project data sets. On here, it's slightly more complicated in that we had 3 different sets of standards. So the LTS, that was the National Tunnel Agency standard. The Lantis standard was the Antwerp tunnels. And it's important to note that before we got involved in the project, 2 of the tunnels had already started being renovated. Before we started developing the standard. So we had different standards at different times. So depending on when you started designing, you'd be using a different standard. But this is where linked data comes in. So you have different sources of requirements, but it essentially pulls together and you can baseline. So at a specific point of time, so say we introduce requirements in the new tunnel standard for ventilation, that can then replace the requirements for ventilation in one of the other previous standards. And so for each project, 20 different projects, you could look at a single point of time and you'll see the baseline and which set of requirements those parts in that project were designed to at that time. And so that was one of the benefits of using linked data. And we use specifically the LACES software, so that's our partner Semtech who developed that. And that enabled us to really track the baselining so that whenever a project was going ahead at different times, it would always use the most relevant standard set of requirements. Okay, a bit about the benefits. Okay, so software independent. A big part of that is future-proof. So we have tunnels that were 50 to 60 years old. We're renovating them. They're hopefully going to last for 50 to 60 years. You would imagine you would want your data to also be future-proof. So what's the point of designing a tunnel and creating a digital twin for it if in 10 years' time, your data is no longer in a useful format? So by having it in a platform that any software can read, or any linked data following software can read, you're really thinking about the future for your data. It's also meaningful to machines. So by having it in that link format, machines can do things like automate. So we needed baselining on our projects, so we have many different sets of standards, but you might have different needs. And because anyone, like on HS2, we had 1,600 people, many different contracts. On this project, we had many different parties. You can have a different party using one software for their needs, and they can tailor their software to come up with innovations or options for them, and then you can use a different software in your part, and all the data will still work together. That also ties in with the interoperability aspect and it being distributable. And so on Flemish Tunnel project, we pulled all the standards together. We just used one, like the designers would just use one single source of truth that was updated as the data became available. But on your projects, for example, you could have 3 different government organisations, 3 sets of requirements, but your designers will only see, and your constructors will only see the set that's relevant to you. And if they update it, you can then baseline yours so that your single source of truth, you'll know exactly where it came from, at what time, and then you'll also know what was designed to those requirements. But the big point I would like to stress here is the innovation aspect of being able to use different softwares and tailor the softwares to meet your needs and not commit to, say, a single software that gives you a single output, for example, doors with a doors file. Conclusion. Enriching model-based systems engineering with interoperability from master data and again with linked data. So what are the key takeaways? So infrastructure and construction and systems engineering projects in general are becoming much more complex. We have more requirements, we have more software systems, we have more integration, we have environmental requirements that are much more strenuous and more numerous. We have safety requirements as well that are becoming more strenuous, operational requirements. The projects are becoming more complex. Model-based systems engineering is a solution to this problem of complexity. And as systems engineers, you might be starting to use this on your projects more and more frequently. The International Standards Organization this year published the standard for model-based systems engineering, ISO 24641. So the industry is also recognizing that to tackle this problem of complexity, we can use model-based systems engineering. But there are still further areas that we can build on model-based systems engineering. Using object type libraries, we can make sure that one person working on one organisation will have the same meaning for their data as someone in another organisation working on the same project. You'll know a track consists of rails because it's in that object type library, and you can avoid a "here comes the sun" thinking your track consists of a Beatles song moment. It also allows a good degree of automation. We saved over 1,200 hours just by automating verification by using that object type approach. And so again, that happens when you have the ability to have consistency across many packages in a machine-readable way, allowing for automation. You can then improve that again with linked data. It's software independent, it's future-proof, and the big benefit is that it fosters innovation. People being able to create different modifications to their software to suit their needs. And thus, for that note, we would encourage more people to use an enriched model-based systems engineering process with the object type libraries, master data, and also with linked data, because the more we all innovate, the more us systems engineers can tackle the problem of project complexity. Thank you all for your time. I hope you learnt a couple of different things. I shall open it up now to any questions.
Okay, folks, so join me in thanking them for their presentation. And we've got a really keen person straight in here with it. Derek, go for it.
Morning, thank you. Derek Price from Network Rail. So we have a similar challenge, but often with brownfield existing railways. I get the technical proposition. I'm interested in the people that were paying for it and funding for this new initiative. What did you find with the touch points in terms of the people paying for it and supporting it, getting value from it? Was it the same as you expected, or did you get any surprises in the things they found useful and worthwhile?
Do you wanna...
So, yeah, I think it's working. So that's it. Thank you for your question. That's a very, very interesting one, and we see kind of different trends, and it has also to do with the maturity of the market when it comes to linked data itself. So when so maybe we separate the question first from the master data perspective. The reuse of information is seen as very beneficial, but also this setup, for example, allowed us to implement changes on a project very quickly. So, for example, we got just the feedback from HS2 that we were the first contractor that were able to implement a whole new set of requirements. So that's some of the feedback that we get from like the master data thing. When it's come from a linked data perspective, I think the value is much more in the whole supply chain. So what we see, for example, in the Netherlands, is that main clients like Tenet, which is the power network supplier for a large part of the Netherlands, but also some provinces, are starting to use linked data and asking the supply chain, us as designers, contractors, to exchange information, design information, in linked data format. Of course, that is beneficial for them because they say, okay, this is where you find all our information, just tap into this. You don't have to go with standard revision and so on. This is this baseline in this linked data format stored on the web. This is where you need to be. I want you to contribute to our design and our requirements from your perspective. And I want you to add to that data in the same format to our database, so that can be used further down in the supply chain. So, and I think that is the feedback that we get back from paying clients, especially on the linked data sites, that they are kind of promoting now the use of linked data. Of course, we solve a problem for them. Of course, it's about exchanging information without all the hurdles. So my suggestion would also be like that the clients are taking a role up to this just by defining, okay, this is the way how we want to exchange future information in the future. Of course, you break down the barriers between different organizations, different pieces of software. What it requires from design organizations like Arcadis, for example, is that we have like standardized our design processes, our systems engineering processes, supported by a information model that includes the semantics. So we can really easily adopt information from a client, map basically the requirements to our design world, but also the output of our design world is easily mappable to what the client is asking for. Yeah, thank you.
Hi, David Byrne, AWE. I've got a question on the numbers about halfway through. I think you had 64,000 requirements, something like that, and you were saving 23%, and it gave you 1,200 hours saving. So a bit of maths there. I think you say it makes about 6 minutes saving per requirement. So where my question's going is, if this is all automating, you're saving 6 minutes per requirement, let's just say there's a bad accident in 20 years' time. How do you justify as a business that nobody looked at these requirements and you saved 6 minutes ago?
That's a lot of numbers. So, sorry, what can you rephrase ask the final bit of your question again?
Okay, the final bit is if something bad happened
and
there's a board of inquiry and they said you took a business decision not to human intervene to save 6 minutes per requirement, how would you stand behind that?
Well, I think there is a human interfere, but the thing is that the human interfere is much earlier in the process. By our actual lead disciplines that have an in-depth knowledge related to to the design. What's probably good to add, in the design process, we have loops, and when we find gaps, we are also improving basically our data. But yeah, I think but I think we just bring it in earlier on in the process. Yeah.
Can I add one thing? Also, sometimes too much human input's also a problem. So if you have the same requirement for the same object type, if you have two different forms of verification, that can be an issue. So the automation, it isn't just like a blanket like, oh, show us your calculation for this bridge, you know, like that would have to be done specifically. But if it's like, for example, you have a requirement that you must develop a plan, if you tag the plan to that work package, you can automate that. So you can like pre-populate the plan into that verification result. So, and again, as Harmen mentioned, there's a human like review cycle of that, like what can you automate? If you're not sure, you probably shouldn't automate it. But it's, if you had someone like putting in several thousand plan names, you're probably going to end up with one of those plan names being the wrong document. So it's partial automation, not full automation, and that's normally better quality as well as the time savings. I think the calculation we did was 5 minutes per requirement. So.
Hi, I'm Kate Habgood from Capgemini Engineering. I noticed that I think the linked data seemed to give you a really good syntactic standard for exchanging data. But in my experience in model-based systems engineering, actually there's often very many different ways of modelling the same information or the same behaviour. And I wondered if you found that a problem to gain that level of consistency, and if so, how you dealt with that. Did you have to standardise sort of the semantic way of modelling across the different organisations?
Do you want to answer?
Thank you for this very interesting question. So I think there are a few developments also on this on the market. So I'm not saying that. So every organization, first of all, has their own processes and information and how they want to assure quality. So I think that's the first one. And as a consequence of that, everyone will have their own ontologies and information models. But the thing is that if you establish that, then you can start mapping other information models much easier to that information model. So that's one. Then I think there is a ideal, and it can differ per project on like how much you can standardize indeed in your model-based systems engineering and how you describe relations and so on. But what you see in the SysML world, and especially with the release of SysML 2.0 now, is that they put in much more formal semantics just to be able to transform those SysML models into meaningful data to also to other systems for the exchange of information. So it's an interesting one, and we're definitely not there yet to with a definitive answer on for which projects and what kind of modeling, systems engineering modeling. It is a solution, but I think you see the trends in also with the SysML language in putting more formal semantics, with introducing the kernel top model, and I get also the demand from clients to have a way of exchanging information that. It will be good if the market and the sector would move to like a linked data approach for the instances where it is possible, and I'm also believe that there are plenty of designs, but also just projects where the exchange of information is less relevant, and therefore the meaning of the way of exchanging information is therefore also less relevant. I hope that answers your question. Yeah, thank you.
Time for one last really quick question.
Hi, Mani Puri from BAE Systems. I just wanted to ask, with linked data, how do you deal with increased sensitivity or classification of amalgamating different data sources?
Yep. So one thing I didn't touch on, there's linked data and linked open data. So with linked open data, there's no security. Like anyone can be free to use those links and access the links. With linked data, it depends on the software, and there's like security controls involved so that you can't just get a link and then have access to a whole project's data. So it is access restricted with linked data, but there is the future possibility of linked open data where it isn't security controlled and it's free to share and reuse across different projects, different organisations. Does that answer your question? I know it was brief.
Okay, then I'm afraid that's all we've got time for on this session. Please join me in thanking them again.